I'm now going to pass back to Chris Coetzee, who's the country manager of Boston, South Africa.
Thank you, Maz. So we're moving quite quickly on to our last presentation before our morning break. Your password for the session is mission. As a reminder, attendees who provide at least 7 passwords by the official close of our event can unlock training given by our Boston Trading Academy this Friday, the 2nd of October. On Thursday afternoon, a form will go live on the same page you registered on. We'll also provide it to you over email for you to input your codes. So without further ado, I'd like to introduce our next session, Green Innovation at HPC. This is a sponsored session, so I want to thank Supermicro for their support in making this event a success. And I'll hand over to Vic Malyala, Senior Vice President at Supermicro.
Hello, everyone. Thank you for joining us at the Boston HPC Roadshow. And thank you, Boston, for inviting Supermicro to present our green innovation and our strategies in HPC to bring the best value performance without any compromise in it, as well as be able to save the earth and keeping it green. Without further ado, I am Vic Malyala. I'm a Senior Vice President here at Supermicro. And as a quick glance at Supermicro, we are a company that is established in Silicon Valley back in 1993. And we have a revenue of about $3.3 billion in fiscal year 20. And we have global operations in about 100 countries. We mostly work through our partners in different regions. As well, we work with strategic customers directly. And we have been ranked in the Fortune 1000. I believe it's Fortune 697 as of last year's revenues. And because of the company as it's scaled over a period of time, the San Jose headquarters has been expanded. Most of the production happens here. We also have manufacturing facilities in Europe, in Netherlands for the EMEA operations. And we have an office as well as manufacturing capabilities in Taiwan for the Asia Pacific operations. Majority of our staff is in engineering. A good 1,700 of the 4,000 people focus on engineering side of it. And we take pride in bringing technology first to market. And most importantly, about green computing that is going to help the enterprises, cloud, artificial intelligence, and other verticals across the board. In the last couple of years, Supermicro has been doing this green data center survey. And one of the things that we do is to reach out to different data center customers around the world. And we collect their feedback as to how they're operating their data centers, how efficiently their data centers are running, what are their pain points, and what are the initiatives that they have in their company to keep the data centers green. And the surprising fact is that a lot of data centers are not necessarily green. About 400 responses that we have received in our last survey, only 12% of the data centers are deemed green. Many of the data centers are running at a very high PUE of about like 1.5 or 1.7 or higher. And one of the things to notice is that in the global electricity power consumption, about 1.5% or even slightly higher every year by the data centers. And running this data center efficiently will help in reducing the emissions quite a bit. In addition to that, as the data centers are increasing, now about 8 million data centers worldwide, a typical data center actually can save 350 tons of e-waste on average if they were to manage the data centers properly. And in many enterprise customers or many enterprises as such, green IT is an afterthought. People often tend to look at the investments that they need to do in making the infrastructure cost effective, but they don't really look at how the data centers are going to consume power and how much the cost comes associated with it. So this is one thing that we have been doing to kind of collect the data and bring it back to the customers and these partners as an awareness as what are the things that could be done to make these things green. Case to point about the HPC market size, which is the focus right now. One of the things that we have seen is the HPC markets are growing tremendously. The worldwide HPC market is about $39 billion, this year, and it's expected to grow about 6.5% a year, and it's expected to be around 53 or 54 billion in the next few years. One of the market drivers, if you take a look at, besides the traditional HPC markets, we're also seeing a lot of initiatives that are coming in virtualization, artificial intelligence, machine learning, and the areas of healthcare and the need for hybrid computing in accelerating these innovations. Think about high resolution weather reporting, a lot of things that were not possible before because the amount of computing that we are able to bring it, people are able to consume, people are able to accelerate innovation. This also gets into enabling in different verticals like public sector, the defense agencies, the academic research and the institutions, national labs and other things. So both in terms of the type of application that are going to be run and the kind of verticals it's going to support is really accelerating the HPC markets, which also means that if we are able to run these data centers more efficiently, the HPC, if we are enabled to make it run more efficiently, it's going to help a lot. So how does Supermicro make this HPC green? One of the things is when you are designing, it needs to start from the roots. So when Supermicro is designing the platforms, it always starts with the core of a motherboard design, and it builds from that. A motherboard, a chassis, a power supply, the backplane, the fans, the certain type of cooling that we need to incorporate. All these things, when it's coming together well, and if you're able to manage this using powerful system management utilities, that is the core of the overall server design, which we are able to kind of expand into different form factors. And when it's deployed from a small 1 or 2 systems going all the way into a data center that's running tens of thousands of systems, and how we scale. So if you go into looking at the design of it, one of the things is as the data center sizes and the deployment sizes are getting bigger, one of the things to look at is the disaggregated server architecture. It's part of our overall resource saving initiative to kind of take a compute, storage, and network elements of a system into 3 different chunks and be able to give an option to upgrade as needed. Similarly, if you're taking a look at systems, instead of having a standard rack mount systems or 1U, 2U pizza boxes, we are able to bring multiple nodes within the same system by means of sharing the resources and be able to extend the savings. And at the same time, by using certain elements of cooling within the system across multiple nodes, we are able to save the cost associated with cooling and run it more efficiently. Last but not least, by picking the right elements in terms of platform design, we are able to extend the platform lifecycle. By doing so, depending on the application, we are able to save up to 50%, in terms of power and cooling. At the same time, by having the use of multiple nodes in the same system and by increasing the density, certain acquisition costs will also be reduced. More importantly, the design criteria actually can help in running these systems at a higher ambient temperature, which also helps in reducing the air conditioning expenses. So when you put all these things together, that is when. Let's take a step into this disaggregated server architecture. If you take a look at the typical blade type of, or any rack mount for that matter, in this case, we are looking blade as an example. So what you see on the left, the compute module is the one where you have processor and the memory. And on the right side is where you have the connectivity module, which is the networking portion of it. And you also have the storage portion of it, which can be part of the same connect module, or it can be a separate one. And what ends up happening in this case is when the processor technologies change, you don't necessarily need to change the storage and the networking and the enclosure, the fans, all these things. So one of the reasons why we are able to do that is to pick the right type of components. For example, if you take a look at this disaggregated server architecture, one of the things that we are looking at is to pick the right kind of power supplies that have a life cycle support of, let's say, 10 years as opposed to typical 5 to 6 years. Similarly, picking the right type of fans and the right type of storage. Nowadays, with the advent of this NVMe and new flash technologies with very high endurance, we are able to extend that life cycle also. So by using this and separating it from the compute, now almost 45 to 55% of the resources are repurposed when you are refreshing from one generation to the next generation. So this actually makes a very good value proposition for people who are looking at any deployment at certain scale. Talking about multi-node power and cooling, this is where if you look at a standard rack mount system, a typical system will have anywhere from 6 to 8 fans and couple of power supplies for for redundancy. When you're talking about a 4U 4 node, all of a sudden, if you were to change it to a twin technology, which is Supermicro is a first to bring the twin technology to market back in early 2000 timeframe. In this case, we are talking about just 2 power supplies and 4 nodes in a 2U form factor. Number one, we are doubling the density. We are cutting the power supplies to 25% of the number and reducing the fans by half. Just by doing so, you're able to reduce both the component as well as the overall cost of the system. And in terms of the power and efficiencies, we are able to reduce the TCOs up to 50%. So talking about different type of cooling that required to run these systems more efficiently, obviously we're talking about keeping everything green here. And if you take a look at forced air cooling, which is typically used in many data centers today, many HPC customers use standard forced air cooling, mainly because that's been there for a long time. And in this case, what we are looking at, as the components get hotter, nowadays CPU TDPs are going to 250, 270, even 300 watts. In order to use the forced air cooling in a dense form factor, it becomes very critical. So what we are trying to employ is the vapor chamber heat sinks in order for us to bring these systems in a forced air environment where we are able to run it much more efficiently, which is not possible by using the typical heat sinks. In this specific case, basically when the plate that is connected to the CPU, in this case, when it gets heated, the heat gets moved away by using the vacuum sealed heat pipes. And as it gets condensed, and when the heating exchange happens, it comes back down. So this way, we are able to extend the operating temperature range for the systems. But it is not always possible to keep the systems operational at this level, especially when the components are going to be using more and more higher TDP, in which case we have to look for alternate cooling mechanisms. One of the alternate cooling mechanisms is liquid cooling. So many data centers today are already using some kind of chillers in order to manage the data center. So what we are trying to do is to bring that chillers and use the cold water to keep the servers cool. So what you're seeing on the left side here is the servers, a typical node that normally uses heat sinks that will be replaced by the liquid cooling instrumentation. So which provides the coolant to be moved between the servers and the top of the rack coolant distribution unit. So within a rack, you have multiple systems with the pipes coming from each server. The heat exchange happens at the top of the rack, which again gets moved through the data center into the cooling tower externally. So outside of the data center with a huge fan kind of dissipating the heat. Eventually, what is happening is we are taking a need for having unrealistic fan speeds and the amount of cooling that need to be created, which is not practical with forced air cooling, and replaced with the liquid cooling solutions. This is more practical in many data centers because the whole cooling can actually be brought at the rack level. However, it is not always possible, and people are also looking at a better way of even cooling by taking it to the next level if they have the ability to have a customization to the next level. In which case, immersion cooling is also used. Immersion cooling is one of the things. What you are seeing on the top left is a deployment that we have done at the University of Vienna. It's part of Vienna Scientific Cluster 3 series. In which case we have used one of the immersion cooling mechanisms. In this specific case, we use GRC, but there are other partners such as Asperitas and Submer. There are upcoming companies that are able to take this innovation to the next level and also provide alternatives. So typical cases, in order to make use of this kind of immersion cooling, if you have a need to cool more than 25 kilowatts, and which is very easy to do that nowadays. A typical rack can go even 60 to 80 kilowatts. It is much easier and cost effective to go with an immersion cooling. Again, now we are talking about 3 different types of cooling here. With standard forced air cooling, how we can make it more efficient for the people in a data center environment where they have somewhat of flexibility, but not a total flexibility. We can use the direct chip cooling. And if you have the flexibility to take it to the next level to really reap the advantages, now we have an immersion cooling. So by bringing all these things into the appropriate environment, we are able to bring the PUE sometimes to less than 1.1 and going all the way down to like 1.06. One of the things that we are seeing is a wider adoption of hybrid or the compute with GPU. So what we are seeing is because of the type of workloads that are coming up and the ratio of the CPU to an accelerator. Let's say GPU is one of the most popularly used accelerator in this case. So the ratio between the CPU to GPU and how the communication between the GPUs need to happen and how many GPUs need to be fit in a given system and what is the power budget that can be allocated per system. A lot of these things come into picture in terms of the platform design. By, again, going with a ground-up approach of starting with giving a flexibility of supporting all these form factors and all these different densities and ratios, we are able to size the GPU platforms properly for a customer needs. This is yet again another value of looking at the problem size and bringing the right platform, so we don't necessarily need to waste any resources that are not going to be used. So whether people are using a standard 1U form factor, all the way going to a 10U form factor where we are able to support up to 16 GPUs with SXM3 connectivity, or taking it to a step further, using it the latest generation of the GPU platforms from NVIDIA. So based on 8 GPU version, which is Delta, or 4 GPU version, which is Redstone, we have designed platforms that are both Intel and AMD based, current generation as well as support for the next generation that is already worked into that. The good thing about this is efficiencies are always improving from one generation to other. By bringing these new technologies first to market and enabling the customers, when they are deploying the new HPC clusters, instead of using a previous generation, which is oftentimes anywhere from 30 to 40% lower performance, we are able to bring the performance as well as the cost efficiencies associated with the platform design and the power and other efficiency factors that are going to help in running these HPC applications much better. In terms of the platforms, another thing that we are also seeing is a wider adoption of dense compute platforms along with a GPU. In this case, what we are seeing is a Supermicro Blade form factor in which we are able to support 20 of a double width GPU or 40 of single width GPUs in a 8U form factor across 20 nodes, in which case we are using the second generation AMD EPYC processor along with a support for either 2 T4s or let's say one of the V100 or even A100 type of GPUs from NVIDIA, or even accelerators such as Xilinx FPGA and otherwise. So again, it's all about bringing the density and the ratios and as well as the high level of integration to bring the right value. As I was mentioning, twin technology is one of the things that makes Supermicro take pride in itself. as we bring the first ever twin platforms to the market by literally cutting the rack space into half by doubling the density. And we have taken it a step further over every generation. And currently in the 5th generation of our twin product family, we have Big Twin, Fat Twin, and Twin Pro. If you are looking at the product, I would say overview, in which case we are talking about 2U4 node, which is the most popular, to a 4U8 node, and even 1U2 node. Depending on, again, what kind of form factor and density customer chooses, we are able to give that to the HPC community. All these things will support up to 200 gig HDR InfiniBand, or going lower to 100, the EDR and FDR InfiniBand, as well as the standard Ethernet protocols supported, whether it's people are using 10 gig, 25 gig, or 100 gig type of Ethernet. So efficiencies, density, different type of connectivity, being able to support pretty much any CPU that is whether Intel or AMD based, that we will be able to support in that, with an offering for a standard forced air cooling, and then liquid cooling, as well as potentially immersion cooling, depending on the customer's willingness and the type of processor and platform that is chosen. So if you take a look at the disaggregation I talk about, that is not just specific to like let's say a blade, but in this case we are looking at a most popular platform, which is a 2U4 node Big Twin. In this case, if you take a look at a single node, how we are looking at the design of it, we kind of separated the network part into an SIOM or AIOM, which is a superset of the OCP 3.2 mezzanine. We are able to support either of them as a standard, think of like a mezzanine that can be removed, which is on the bottom left you're seeing there. Also, these things support a couple of add-on cards, in which case it's a standard low profile add-on cards, which can be used and upgraded based on the customer needs. Again, as I said, from 1 gig going all the way to 200 gig. And for the local storage point of view, you can have a SATA DOM, or you can use an M.2. And compute portion, you're talking about different type of processors, whether it's Intel or AMD based. So if you take a look at what is happening here is that each node is serviceable by itself. The cooling is shared. The parts can be upgraded and changed based on the requirements and what can be supported. So people have to look at a different way of how do we figure out a way to use the systems in a way that can save the CapEx as well as OpEx, not just on one generation, but refreshing over multiple generations. So this is the type of philosophy that we are expanding and extending to different product lines over a period of time. Again, talking about density, SuperBlade is one of the key product line for Supermicro. It's offered in a 4U, 6U, or even 8U enclosures, depending on what kind of processor that people want to use and what kind of network level redundancy that people are expecting, and what's the cost factor that people are looking at. So based on this, we have anywhere from a single socket all the way to 4 socket, and different form factors and different switches and redundancy in management and all that we are able to support on this. And we also have MicroBlade, which is think of a small brother of the Big Twin, the SuperBlade, in which case we're talking about a 3U and 6U enclosures, again, providing unparalleled density as well as the real optimized value for different customer applications. All this discussion will not be complete unless we look at NVMe as a part of the storage. Storage is one of the critical factors in keeping the HPC community running their applications quite well. So if I were to rephrase it, when you take a look at all these HPC clusters, we need to provide the data the quickest way that's possible for the CPUs and GPUs to churn the data and then run these applications. So again, depending on what kind of IOPS, what kind of latency, what kind of redundancy that is required, and what kind of long life cycle that people can expect, all these things based on that, whether you're looking at BGFS or Lustre or Veka, whatever the file system, we are basically validating all these things on our NVMe-based platforms, and we have various platforms that can provide quite compelling and while cost-effective and extremely high performant, and more importantly, you are able to reduce the footprint of the rack quite a bit. For example, if you're taking a typical hard disk drive based storage, multiple racks can be consolidated into less than half a rack to get the same performance. Of course, when you look at the capacity and other requirements, then you can pick the right platform and enable the HPC applications with the right type of storage. So that's yet another value. Storage and compute kind of bringing it together to provide the right value proposition. So these are all the stuff that we have been doing in terms of platform design and how it fits into a rack and into a data center. What are the different types of technologies that can be adopted in making sure that these are easy to operate, keeping the cost to the cost-effective manner and lowering the total cost of ownership, operating the data center efficiently and all that. So I want to give some examples on some of the areas where, in the interest of time, a few examples I'm going to give. So one of it is the Green 500 ranking. So if you take a look at every 6 months, we have top 500 during supercomputing event. And when you organize this, reorganize these top 500 based on efficiency, you get Green 500. So the most recent supercomputing event, we are able to demo or showcase our collaboration with Preferred Networks in bringing the first ranking Green 500 system. Credit goes to Preferred Networks for making a very high performant accelerator and a platform with MN3, and Supermicro for bringing the right system to go along with it. Overall, we are able to deliver the right performance in the most efficient way. So this is an example of how the design strategies that are being employed by Supermicro is actually working in a real environment and how people are able to innovate together. Another example is in a university environment where we are able to deploy an HPC solution. And nowadays, because of a lot of innovation happening in terms of medical research, we are able to deploy this for both COVID as well as physics research, in which case we are actually using an AMD second generation EPYC in our GPU platform. 8 of these GPUs, which are AMD Radeon Instinct MI50 GPUs, are being used. And again, bringing the performance and keeping the design simple. In this specific design, we are able to eliminate any need for any PCI Express switch. So the CPUs are connected to the GPUs without any additional latency or complexity. As well, we are able to support up to 400 gig of the network connectivity to move the data in and out. Yet another example is I talked about SuperBlade and MicroBlade in the previous few slides, and the reason we have designed these platforms the way is to help the customers to increase the density, and people who have the ability to take advantage of it, they can really stand to reap the benefits. In this specific case, we worked very closely with Intel in developing these MicroBlade and SuperBlade disaggregated architecture, which is being used in Intel. A little over 200,000 systems have been deployed, and you can see one of the aisles, thanks to Intel for providing access to this data center to take a picture. But this particular one is where you can see about 30,000 systems in each aisle, and quite impressive deployment. But it is also powered by a disaggregated solution that is provided by Supermicro, thanks to our Supermicro, SuperBlade, and MicroBlade. And in this case, they're able to run the data center at 1.06 as a PUE and be able to operate the data centers extremely efficiently, as well as because of the disaggregated hardware, they're able to refresh over a period of time. We don't need to necessarily get rid of all this e-waste after every 2 or 3 years, but you can repurpose it over multiple generations of the processor as well as the networking refresh. Yet another example is the deployment in Lawrence Livermore National Labs. This is based on the Intel Xeon, second generation. So in which case we are able to, use the standard Supermicro 2U4 node Big Twin platform, again bringing the performance and cost advantages to the HPC. Another example is NASA for climate simulation, in which case, again, we are going with a 4U8 node, in which case it's a Fat Twin platform, again going with the Intel Xeon in this case, to bring the advantages of using bigger fans for efficient air cooling and density, and repurpose and reusing much of the sheet metal across multiple nodes, which is sharing the resources. The whole thing actually able to provide the right density as well as the performance, while without any compromise in performance, and keeping it very efficient. And one of the things that we also take pride is in providing very efficient gear to help with black hole event horizon imaging for the Max Planck Institute. So we are able to again bring our twin technology as well as a storage system together to host a big amounts of data, as well as running this very efficiently. So the point is, what is the winning edge here? We all need to win. I mean, number one, we all need to survive on this planet Earth, and we need to keep the Earth green. And this is one of the fundamental driving forces for Supermicro to keep the IT green. And while to do that, we have to think about running this environment, this data center environment very efficiently, starting from the core, which is the design of the platform, going all the way into a rack level and at a data center level, and how we work with the partners to bring the efficiencies into the equation. At the same time, how do we extend the life cycle of these products over multiple generations? That way, we are able to reduce the e-waste. And by doing the whole thing together, we are also able to reduce the cost. So it's a win-win-win situation all around. So we are able to bring the right CapEx and OpEx values and be able to refresh our generations. And most importantly, we are able to keep the Earth green and innovate quicker without any compromise on performance. Thank you for attending the session, and thanks again to Boston for inviting us here. At this point, we are opening it for question and answer session. You can click the button on the top right and ask the questions, and we will try to do our best to answer your questions.
Vic, thank you very much for that. So we'll open up the floor for questions. Both Vic and the local country manager for Supermicro, Valent Monner, are available for questions. Maz, I hand it over to you.
Hi guys, yes, so please get your questions in. You should be able to see the little Q&A tool that's at the top of your screen, or if you're joining via the web app, I think it's in the center of your screen. Okay, so I think there's a question for both of you, really, Vic and Wayanand. What do you think is going to be the next leap in green innovation?
So this is Vic. I'll take it. So when you look into the processor roadmap as well as the connectivity side of it, one of the things that we are seeing is the amount of data that need to be handled, the type of data sets that need to be handled is getting bigger and bigger. And that also is a part of at what resolution we are taking a data set and running. I mean, if you take a look at autonomous driving as an example, the amounts of data that's being generated and that need to be processed, and a decision need to be made, or a training models need to be developed. So if you just imagine the amount of data that need to be handled, it's a lot more than what it was at some point of time ago. If you look at the processor generation, what is happening is as processors get evolved, the next generation we're talking about PCI Express Gen 5 or DDR5, and CXL as a part of it, which allows the accelerators and the GPUs to access the main memory through a coherent connectivity. All these things are going to help managing bigger data sets and be able to process complex workloads easier. So when we look at it, the scientific community has access to powerful compute equipment, which also helps them to innovate and try to bring more parallelism into the equation, and be able to handle complex problems. Whether it's whether research or more relevant right now is medical research. All these things. The way I look at it is, more accelerators are going to be part of the HPC ecosystem, and the systems do need to run more efficiently. Things are going to run hotter, and as the companies that are making these products, we need to understand what kind of these balanced architectures that people would be making use of to take on specific type of problems, and we need to enable them. So the way I see it is, it's bigger, faster, and more powerful. At the same time, they need to be more efficient.
Fantastic. And Vic, I was wondering, could you tell us more about the green facility in San Jose? I know that I've had the pleasure of visiting it myself, but I know that Supermicro are practicing what they preach with a number of kind of new green and eco-friendly buildings.
So one of the things that we are looking at is, being in Silicon Valley, it's a lot of emphasis is put all around for green, whether starting with Tesla as a car, or having data centers running more efficiently. So one of the things that we are looking at is, it's not just for data centers, but also when you are doing the manufacturing of the equipment, we need to make sure that it runs efficiently. Typically in a building's point of view, changing everything to more efficient LED lighting and things, that is only part of it. But also we use basically, I'm trying to remember the name of the company that we work with, effectively to turn the natural gas into electricity with the minimum, I would say, pollution per se, compared to the traditional alternatives, and also employ any kind of solar and other alternate electricity that we could be generating in all our buildings and whatnot. So we are looking at running our buildings more greener, and our production cleaner, and automate in terms of moving the equipment from one location to other, and all that through some kind of robotics and whatnot. So all these things are employed in different scale as we continue to expand our facilities. I think those are some of the things that we are doing to from Supermicro's end to keep it green.
Fantastic. And people can visit the Supermicro website to download the Keep It Green white paper as well. And Chris, did you want to close just with talking about Boston and Supermicro's relationship in country?
Sure, yes. So what we try and do as Boston Limited locally is we try and replicate the strategic global relationship between Boston and Supermicro locally. So we work very closely with Bainat and his team locally from a commercial as well as a technical perspective. We enjoy chatting to them about where we're going, working with them on opportunities, and we're very proud of our relationship with the Supermicro guys.
That